In the videos this week, we will go through an example of how to calculate a correlation coefficient and also how to calculate a best fit regression line. We will look at some data from a sales company that relates the years of experience of their salesmen to their annual sales. We can see just by looking at this data that as the years of experience of the employees increases, so do the annual sales. We should already be able to tell that there is a positive correlation between these two variables. Here we have a graph of the data pairs called a scatter plot. We have a scale on the x-axis for the years of experience and a scale on the y-axis for the annual sales. Plotting the 5 data pairs we have from the table gives us a better visual representation of the correlation of the data. If the data had a perfect positive correlation, the points would be in a straight line, going up from left to right. We can see here that the points do not line up perfectly, but there is a somewhat linear correlation between them. To quantify this correlation, we can calculate what's called the correlation coefficient. That is a number that ranges from -1 to +1. The closer the correlation coefficient is to a +1 or a -1, the closer the points would be to lining up in a straight line. A positive number for the correlation coefficient means that as x increases, y is also increasing. And a negative number would mean that as x increases, y should be decreasing. A correlation coefficient of 0 would mean that the data was scattered and there was no relationship between the two variables. Here we can see that our data should have a positive correlation coefficient because as x increases, which is the years of experience, the sales also increase, which is the y variable. We should also expect it to be fairly close to 1, since the points seem to be in a fairly straight line. Calculating the correlation coefficient, which we use the variable r to represent, is very tedious to do by hand. However, it is good practice to make sure that we understand all the symbols and how to use all the formulas that we have in statistics. Before we get to that formula in the top right corner, we should realize that there are 5 summations that we need to calculate in order to use that formula. The summations we use are very similar to the ones that we have in the standard deviation formulas we saw last week. The 5 sums that we need are the sum of x values, which we can calculate in column 1 of our table. We need the sum of y values, which is in column 2 of our table. And we have column 3, which we use to get the x squared values, just like our standard deviation formula calculation. Column number 4 has the sum of y squareds. So I took all the y values, squared them, and then added them up. The last column is the sum of x times y. And what I do is I calculate x times y first for each data pair and then sum those 5 values. Once we have those 5 summations, we insert them into the formula. The key to using this formula is to break the calculation down into 4 parts. For the first part, I'm going to calculate the n times the sum of xy. So we know the sum of xy is 4,280, so I would do 5, since I have 5 data pairs for n, times 4,280. That gives us 21,400. The second part of the calculation should be the sum of x times the sum of y, which from our table would be 35 times 550. That would give us 19,250. I can then subtract those 2 values in the numerator to give me a numerator of 2,150. The third part of the calculation is a little bit more tricky. I want to do n times the sum of x squared minus the sum of x's squared. These may seem familiar to you from the standard deviation formulas last week. I want to plug in those values from my table and make sure that I use order of operations. So the sum of x being 35, I want to square that value. And then I also want to do the multiplication of 5 times 343, 343 being the sum of x squareds. I do those two multiplications and then subtract. That should yield me a value of 490. Eventually I will take the square root of that value. The fourth part of the calculation is similar to the third part, except it uses the y variable. So again, using order of operations, I want to make sure I do the sum of y squared, 550 squared, and also 5 times the sum of y squareds, 5 times 62,500. I do those two multiplications separately and then subtract them. That should yield me a value of 10,000. I recommend trying these calculations on your own and making sure that you're getting the same numbers that I am on the screen. These four values now are the ones we're going to work with to finish the calculation. If I take the square root of 490, I should get 22.14, and the square root of 10,000 would give me 100. I multiply those values together and I divide them into the numerator, 2,150, and that should give me a value of 0.971. The final value of r, 0.971, tells us there is a strong positive correlation between these two variables, since that number is very close to 1.